Hello everyone, welcome back to the lecture series of Learning Theory of Automata and Formal Languages. My name is Binayak Parashar. I am working as an assistant professor in the Department of Computer Science and Engineering at Ajay Kumar Garg Engineering College. So, this is your lecture number 15 and we are into unit number 2. Till now we have summarized and we have tried to cover in unit number 1 the basic concepts regarding the finite automata. We have tried to understand a lot of things regarding deterministic finite automata, non-deterministic finite automata, their equivalence property. Also, we have tried to check that how a finite automata can be also considered with output, that is Mealy and Murray machines. So, these all topics we have tried to cover up in unit number 1. And in unit number 2, we have tried and we have start off with the concept of learning how a expression or how a representation can be done for a given language. And language here we are considering finite regular language which is acceptable by automata, that is known as finite automata, correct? So, I think in the 12th lecture I have mentioned about how a regular language can be represented or how a regular language can be categorized. It can be categorized into 3 ways. One is your acceptor, another one is your generator, and the third one is your representator. Acceptor means the machine which will accept that language. Representative means the one which will represent that particular language, that is nothing but regular expression, and generator is the one which will generate the strings for the given language, and that generator is nothing but regular grammar. So, overall if we look into the entire scenario, acceptor part, that is accepted by a finite machine and all, we have seen in unit number 1. Representator part, that is for nothing but how a language can be represented, that is regular expression, we are looking into unit number 2. And the third one, that is generator, which is nothing but how to generate a string, that is regular grammar, which we will be looking in unit number 3. Okay. So, let's start off with today's topic. Today's topic we will be learning about finite automata to regular expression using state elimination method. Okay. So, in this particular concept, we will try to understand how we can convert a given finite automata to a regular expression. In the previous video, we have tried to understand what are the basic identities of a regular expression, and if we are given a particular expression, how to prove that. But here we will look how to convert a given finite automata to a regular expression. So, let's check the first slide of our today's session. Here we will try to understand the methodology, the basic methodology based on which we will be trying to convert a given finite automata to regular expression, and that methodology is known as state elimination method. Okay. It constitutes basic 3 rules, okay, or you can say 3 steps in order to conceive this particular concept. First one is, this method involves the following steps in finding the regular expression for any given DFA. The first method says that, the first rule says that initial state should not have any incoming edge. Initial state should not have any incoming edge. Let's check it out, that this is one particular state where you can see here, this is your initial state, right? And in the initial state, this is your incoming edge. So, this kind of scenario will not be accepted in step number 1 or rule number 1. So, how to overcome that? We can overcome that by making this state as a normal state. See, and then just do the replication of it. Done. And then introduce a new state which is an initial state and do an epsilon transition to that particular state. I think it's clear. So, this is how you need to do it. Okay. Once you do, then we can say that after the final diagram, after conversion here, can you find any kind of state, any kind of initial state which is having incoming edges? No, there is no initial state. You might be thinking that this is also an incoming edge. So, do not include that because that is a representation part of an initial state. Okay, don't look at that. Other than that, these are initial state, these are incoming edges. This one is an incoming edge. So, we have replicated how? By making this as a normal state and introduced a new state which is a new initial state by taking an epsilon transition. Okay, let's go to rule number 2. Rule number 2 says that now we will consider the final state. Final state should not have any outgoing edges. Now, we will look into outgoing edges. If you look into this given diagram, this is your final state, and this final state is having an outgoing edge, right? So, we need to eliminate this. How? Just make this final state as a normal state, and from this normal state, see, from this normal state, do an epsilon transition to a new final state. and this will be your new final state. This is how you need to do it. Okay, whatever outgoing edges will be there, for them you need to make this as a final normal state, and from there you need to do an epsilon transition to a new final state. Okay, so this is your rule number 2. Rule number 3 says that other than this particular rule 1 and rule 2 is done, then just eliminate other states except initial and final. Okay, and then you will get the final expression. Okay, so this is the general algorithm for state elimination method. Let's check some of the examples to solve it. Let's take first question. First question says that this is the given diagram. We need to convert into a regular expression. I have mentioned all the states because this is a very preliminary diagram. If you look into this question, is there any incoming edge to this initial state? See, no incoming edges, therefore no changes. I have mentioned here, in the initial state has no incoming edge, does no change. Is there any outgoing edge from the final state? There is no outgoing edge from the final state. So, what it will be? It will be remaining same, correct? So, final state has no outgoing edges, does no changes. Now, what is the third rule? Third rule says that other than the initial state and the final state, delete or eliminate other states one by one. Is there any states left out apart from initial state and final state? No. Therefore, we can make this as 1. How do we make this as 1? See. Okay. If you look into this, these 3 input transitions are going into the same direction. We have already done this. That means we can make it as a single and make it as A plus B plus C. Okay. What is this, the expression? Or you can write down A comma B comma C, which is nothing but A plus B plus C only. So, this is how you can convert a given expression, given finite automata regular expression. Let's look into the next question. Next question also gives somewhat like a similar type of question, but here if you look into the first step, there is no incoming edge to the initial state. So, the concept will remain as it is. Clear? If we look into the final state, there is also no outgoing edges from the final state, therefore no changes. So, therefore, finally we need to do the expression, right? Third rule says that eliminate other states one by one. So, I have to eliminate this particular state. So, if we eliminate this state, what will be the diagram? Let me name it as A, B and C. So, therefore, I will be having a C and I will having only one transition. See, I have eliminated this. If I have eliminated this, then A dot, why dot? Because it is having a different transition from a state. A dot B to the power clean closure. B to the power clean closure. Why B to the power clean closure? Because it's a self loop of B, right? Then dot C. So, therefore, this is the final regular expression for this equation, that is A B to the power whole clean closure C. Let us go into question number 3. Question number 3 says like this. This is the given question or given diagram. Now, we need to convert this particular diagram into regular expression. Let us check it out that whether any initial incoming edges is coming to the initial state. Is there any incoming edges? Yes, there is an incoming edge. So, what I will do? I will make this initial state as a normal state. I have made it and just done the replica of it. The same I have copied and pasted, and there is an epsilon transition which I have taken as a new state. So, earlier it was A, B and C. Now, it will become a new state Q naught. Okay. If you want, you can name the states. It's completely dependent on you. Okay. Now, let's go the resultant part. See, if you look into this entire diagram, is there any, in the second step, is there any outgoing edges from the final state? No. Therefore, the diagram will remain as it is. Correct. The diagram will remain as it is. Now, if we want to delete it, so this is the step number 3 part where I have mentioned as Q naught. This is A, this is B and this is C. Correct. Okay. So, therefore, if I have to delete this particular states, I can choose any one. I can choose A also, I can choose B also. It completely dependent on you, whichever you want to delete. Okay. Suppose I want to delete A. Suppose I want to delete A. If I have to delete A, if I have to delete this portion, if you look into this diagram, this is going in this way. Correct. So, therefore, I will make the initial state Q naught and this is directly going to whom? Which state? It is going to B number state, where B was already having a self loop of C, and this will be remaining as it is D, and this will be your final state, correct? Now, can anybody just guess how the structure will be? You can just pause the video and can think of it. See, this is the way it is going from Q naught to B, epsilon dot B, epsilon dot B. I hope this particular concept is clear. Epsilon dot B. But one more thing you need to look into. This is also present, right? From B state, there is a transition for A going to A, and again it is entering into B through B, correct? So what I will do, I will take a self loop over B and then mention what? A dot B. See? A dot B. And it will act as a self loop if I delete A. Clear? Now this is the final diagram after deleting A, correct? So if I have to delete now B, first of all what I will do, before deleting A, before deleting this state, you need to find out or need to check whether more than one number of self loops are there or not. If it is there, then combine them together. Okay, let me combine it. Let me combine into one. Okay, if I combine into one, okay, if I combine it into one, then it will be C. Earlier it was C and here it was AB, right? So both are going into the same direction because it is coming out from B and entering into B only. So I will write down as C plus AB. So this is the self loop part. Now you just look into this diagram. This is somewhat similarly. I need to just delete B, then A dot B to the power clean closure C. And the same diagram it is here also. See, this dot this one whole to the power clean closure dot D. Therefore, the final answer will be what? This will be your Q naught and this will be your C, and there will be one transition where epsilon dot B means what? Epsilon stands for 1. So, it will be B dot C plus AB whole to the power clean closure dot D. Therefore, the final regular expression will be what? Final regular expression will be B C plus AB. It is not mandatory that you need to show the concatenation operator. You can skip this concatenation operator also while writing the regular expression, doesn't matter. If it is not mentioned over here, then you need to assume that yes, definitely we are having a concatenation operator over here. So this is all about the regular expression. How did I calculate from a given diagram? So this was the given diagram, and from there I got the regular expression as this one. Okay, so this is all about your example number 3. Now let us go with one more example, and the next example is question number 4. It says this particular question. Now let us do one by one. There is no steps, nothing. We will be doing in order to do a very good solution in an examination point of view. You need to mention all the steps very clearly, and you need to showcast all the things. If there is an incoming edge to an initial state, you need to showcast over here. If there is a outgoing edge from the final state, that also you need to showcast after deleting. Or if not, then draw the same diagram. And then thirdly, if all are done with step 1 and step 2, just eliminate all the states. So you need to mention what are the states you are deleting step by step. In the first step, I have deleted A. In the second step, I have eliminated B. So this is your number 1, this is your number 2, under step number 3. So everything should be clear and precise. Okay, let's check this question. This question says like this. First we have to check, is there any incoming edges? Yes, there is an incoming edge, right? Okay, and initial only final. So the work finish over here only. There is an incoming edge and there is an outgoing edge also. So I have to make this as a normal state for sure. Okay, so let me do step number 1. Step number 1 will be what? Initial state should not have any incoming edge. So I will make Q naught as an initial state, and from here I will make an epsilon transition and make, suppose this one is A and this one is B. I will make this A as a normal as a final state, because I will show step by step. Okay, and here it will be a 0 self loop, and here it will be the replica of it, 1, okay, 0, and here it will be 1. So this is how I got it, step number 1. If you look into step number 2, I have to make, since final state has one outgoing edge, so I have to eliminate this. We are not going to eliminate this, we are going to make this as a normal state and introduce a new final state. Okay, and make a new final state, correct? And rest will be similar. So it will be 0, it has a 1 transition over here, B 0 1 transition. I got it. So step 1 and step 2 are done. Now we need to eliminate all the states one, other than initial and final. We need to eliminate the other states. The best option of looking into this is just eliminate this part. Then only we will be remaining with this. So if you look into this particular scenario, is it not like a self loop type? See, from A there is a transition going to B, there is a self loop, again coming back to A. So if I eliminate B, suppose, so step number 3, if I eliminate state B, if I eliminate this state, then it will be looking like this. See, I am having a state, I am having this initial state, I am having this final state as well. Okay, and I am having A over here, and this is your epsilon transition, and this is your epsilon transition. A was already having a self loop of whose? A was already having a self loop of 0. Okay, now if I eliminate this part, then it will be C1 dot 0 to the power clean closure dot 1. So again a self loop will be coming over here. What will it be? 1 dot 0 to the power clean closure dot 1. I have eliminated B. Now what I have to do in step number 4? In step number 4, I have to eliminate state A. So if I eliminate state A, now the transition will look like this, Q naught, okay, and directly it will go to QF. Okay. Now before that, what I have to do, before this step I need to combine these two into 1. So if I combine these two into 1, what it will be? 0 plus, correct? So if I just simply write down here as 0 plus, correct? So this is, see, 0 is coming over into the same transition, right? So I just need to eliminate this particular. Okay. Now if you look into this, we are done with this part. Now what is the final answer? Epsilon dot this whole to the power clean closure dot epsilon. Epsilon dot 0 plus 1 0 star 1 whole to the power clean closure dot epsilon. Therefore, the final regular expression, final answer will be what? Final answer will be 0 plus 1 0 star 1 whole to the power clean closure. So this is the final answer, 0 plus 1 0 star 1 whole to the power clean, because epsilon stands for what? 1. So this is how we have tried to make. Step 1, I have eliminated whatever incoming edges are there. How did I eliminate? I made this A as a normal state, okay, and then I have introduced Q naught. Normal state means it was already a final state, so I made it left it as a final state. I have just eliminated the initial state concept from here. Then again in the step number 2, I have eliminated the outgoing edge. For the outgoing edges, I have eliminated this A from the final state to a normal state, and I have introduced a new final state by making a epsilon transition. This means what? This means that A and QF are both equivalent, are both equal. Okay, epsilon means what? There is no transition. After that, what I have checked, I have tried to delete B. I have deleted B. I got this result. Then I combined both the self loops into one, and then I eliminated the last state, that is A, and finally I got this expression. Okay, so I hope in this particularly in this entire videos, we have tried to understand 3 questions. Okay, and in these 3 questions we have tried to understand the concept known as state elimination method or loop elimination method, where I have converted a given finite automata to a regular expression. So in the next video, I will come across with one more important topic, and let's check it out in a proper way. If you have skipped any of your video, then please look back to the previous videos. Okay, thank you everyone.